All right, thanks for coming, everybody. So how's your Spark Summit so far? All right, a lot of good energy here. So today, I'm going to talk about a new technique that we're experimenting with at Zynga. It's inspired by DNA microarray analysis, and we can use it to make predictions on users based on their clickstream actions. So let me dive into exactly how we can apply this. A user installs one of our games. We capture their actions during their very first session, and then we make a prediction about whether they're going to come back in 7 days or not. So this talk's going to go over how we can do this with this new technique. So a quick word about me. I'm a software engineer, and for the last 6 years, I've worked on ML infrastructure at Amazon and now Zynga. But I also went to grad school for stats, and occasionally I'll dip into the data science world and use the tools myself. So all the data scientists here, I can feel your pain. I'm currently the tech lead for ML engineering, and I'm based out of our Toronto office. And Zynga is a mobile video game company. Our headquarters is right down the street here. Our mission is to connect the whole world through games. And if anybody gets bored during this talk, feel free to download one of the games, see if you can win a few hands in poker. But it's not just the game designers that get to have all the fun. We have a long history of applying analytics to the game development process. And this is an overview of our infrastructure for making batch ML predictions. I think it's fairly common. So we start off with our data in a data warehouse. And then our lucky data scientists get to use Databricks to utilize Spark, generate their features, train their models, come up with predictions, and then they push out those predictions to our data services system. And our data services system provides these predictions out to our game clients at a very low latency. So over the years of working with ML systems that look much like this, I've noticed there's one aspect of developing ML models which is much harder than the rest, takes the most time. And that's generating the data. So when you're a data scientist and you have your PhD in math or stats, it doesn't come with a bunch of training in SQL, and generating these features can be very hard. However, it's a very important step. The quality of your data is often going to dictate the quality of your model. Like the old adage says, garbage in, garbage out. So why is it so hard to generate features? It's a lot of manual work, and it takes a lot of tribal knowledge. You have to interpret your features, select which ones to use, select how to capture relationships between different features, and then encode all of these using your data generation language like Spark SQL or Pandas, regular SQL. And Clickstream Data is particularly hard to work with. So by Clickstream Data, I mean a log of user actions. I have a couple of examples right here. So at Zynga, we store our user actions using a hierarchy. So I have an example of leveling up here, and it's part of a category called game actions. Purchase is part of some other category. So these have two different shapes and different values. This is often going to be your most raw form of data, and it can be used to go into daily aggregations later on. That's often easier to work with. So there's 3 reasons why it's so hard to work with Clickstream Data. The first is that it's messy. The log files are huge. It's usually going to be your largest data set. There's thousands of different event types, and each of these events can have different interpretations and structures. So at Zynga, it's particularly challenging. We have many games, and each of these games have their own catalog of features, their own taxonomy. Now, to make this easier, there is, you can use documentation like an event catalog, but it's easy for the actual code to not line up with what's in your documentation. In our case, we have a lot of different versions of our clients out in the wild that might not line up with the current version of your catalog. And then there's just plain old errors, poor documentation, et cetera. So it can be really hard to work with this data just to get all the interpretation. So to keep the audience engaged, I figured we could look at some linear algebra. Hopefully everybody knows what this is, all the statisticians anyways. What we're looking at is an equation for linear regression. And the thing I want you to take away from here is the matrix that represents user features. We have a different row representing each user. And each user has the exact same columns, different values, but the exact same columns. And that leads us to our second problem. Clickstream data is a sequence. So how do we get this sequence to look like a matrix like that? Every user had different events during their sessions. Every event might have different shapes, different structures, different values. So it can be a real pain putting it into the right shape that our models like linear regression expect. And the third problem is that Clickstream data is inherently temporal. You get a timestamp with every single action. So I have an example here of a really naive way to translate battles into a feature matrix. We have one row that represents the number of multiplayer battles that happened, another row that represents the number of single-player battles. But what we lose here is the trends over time. Are the users, is that particular user increasing their battles or decreasing? And you also lose the relationship. So imagine someone installs one of our games, and the very first thing they do is play a multiplayer battle. That tells you a signal. Maybe they installed the game to play with their friend. Maybe they're a competitive type of player. So by simplifying the data into a simple count, you lose that temporal information. So that's kind of what our traditional solution will look like. We'll produce a matrix like this in which you've selected some of the events and you've aggregated them over a specific time period. And you just end up with a whole bunch of kind of like arbitrary events generated for each user. And the way we get there is by using our human interpretation of each of these events, typically hand coding all of the events. And we can add temporal information. You can add a column for week-over-week battles, day-over-day battles. You can add another feature for a specific relationship, which event happened first, or ratios of different events. But that takes more time. That blows up our feature space. And it just makes it harder to do. So there's some problems with this traditional approach, which is that it takes too much time. There's a lot of repetitive work in writing all the SQL code. The more code you have, the harder it is to debug, to maintain. And then despite all of that work, we're still missing some signals by handpicking them. We can't just pick the entire universe of features out there. And what about deep learning? So the trend with deep learning is that it can do very well on high-dimensional data by extracting higher-level features out of our raw inputs. So with facial recognition, we start with a very high-dimensional image. And our different layers in a deep learning neural network can extract slightly higher level features like edges and corners. It can then pick up higher level features like pieces of ears and eyeballs, and finally put it together into a full face. However, how can we use this with something like Clickstream? A Clickstream isn't an image, and it's an event of data. Or it's a bunch of events. It's a sequence. So there are deep learning systems that can work with this, like RNNs and LSTMs. It's an area of active research, though. They're not quite out-of-the-box solutions, definitely not as easy to apply as your linear regression. So that's an up-and-coming area, but they're still kind of tricky. So the solution that we're experimenting with is basically translating each user's sessions over some period of time in the Clickstream data into a user heat map, into this image-like structure that we can use as a feature set. So we generate a heat map for every single user over some period of time from our Clickstream data. And this is what the heat maps look like. We have an example here where the different rows represent different actions, and then different columns represent time periods. So each cell represents an intensity of the action in that specific time period. And each of these heat maps basically tells a story of what a user did over this time. So in this example, the user started by having a few battles, and that ramped up between the 0 to 15-minute mark. They leveled up in the 5 to 10-minute mark, but then they hit an error at the 15 to 20-minute mark. And we can use these features, these heat maps, as features in our regular modeling workflow. So we start off with Clickstream data, then we go on to generate our heat maps, and we can feed this into a model to train it. We can feed it into our trained model to get predictions. So the advantage of this is that with a bit of upfront work, we can have some code that generates this heat map for us. And that takes care of those 3 problems that we highlighted before. It takes care of the mess, because we don't have to manually interpret the events. It's automatically grabbing all those events, putting it into the heat map. It's the right shape for our ML models, and it also captures some temporal information. So you can see trends. You can see battles increasing or decreasing over time. And it's easier to apply than those advanced sequence learning methods that I also mentioned. So now that I've given you an overview of what the solution looks like, I can give you some more information about how you could apply it yourself. And there's basically 3 steps to the methodology, 3 design decisions for applying this in your own system. The first is to pick the time window you want to study. So in our case, we looked at 30 minutes after a user installed the game. And you have to choose how to break that up into different intervals. We broke it up into 5-minute intervals. However, there's no need for it to all be uniform. You could start off with finer grained information to start, break things up into 1-minute windows, 30-second windows, whatever, expand that to 10-minute windows later on. So that's one of the very first choice you have to make when you develop this. The second choice is figuring out how to calculate the intensities. So we're aggregating the events over each time period. And the simplest way to do an aggregation is simply count the events that happen. And that's what we did in our proof of concepts. The advantage of using the count function is that you don't have to interpret the event at all. The disadvantage is that you lose some information. So if you're simply counting the number of purchases somebody made, you lose how much they actually spent. So it might be worth it to select a few high-value actions and actually choose a proper aggregation function that gives you a higher signal for those. Once you have your intensities, you have to normalize them. So you don't want, I guess, one event to dominate the others. The way that we did it was we aggregated the events on a per-user basis, and it kind of gave you more like relative intensities of events compared to each other. You could also normalize things kind of like on a per action basis or across users. You also can scale the actual intensities. So we scaled things down into 8-bit values. So there was no need to capture coarser-grained information about the intensities. The final choice for implementing this is the thing you have to do is limit the number of events. So in our case, when we started off and generated these heat maps using the entire set of events in the catalog, we had way too many. We ran into some issues with Spark, and it's a huge use of resources as well when you have these huge heat maps for every single user. And there's a couple ways you can do this limitation. The first is to limit the hierarchy of events, roll things up to just a couple of levels. So if we were making features for our car racing game, CSR2, instead of having a different action for every single model of car that could be purchased, you can just look at the number of cars across all different models. But even once you've limited things in terms of the hierarchy of events, you also can whittle it down a little bit more by selecting say a top 500 or top 100 events. And for that, you need to evaluate how important every single event is. So this is something that decision trees do, in which they choose kind of the amount of information every feature has. So I'd encourage you to look at that literature to whittle things down and select which events are more important than others. For example, you could run random forest on the raw data and then just look at the top 100 events or whatever from there, limited to that. And once you've made all these design decisions for how you want to capture your heat maps, you have to go on to implementation. So for us, we used Spark, of course. And the advantage of using Spark is that we can programmatically generate our features as opposed to a declarative language like SQL. So once we developed this framework, we could generate our heat maps for any of our games. And this is a big advantage for us. Traditionally, each game has its own taxonomy, its own set of features. And so if you wanted to make a likelihood to churn model for one game, you couldn't really apply those features to another game. So this is a big productivity boost. So once you have your heat maps, you'll want to do some modeling. However, there's one trick we can do first. So I think it's already obvious that there's relationships between data, between columns. So columns represent temporal information. If you have an event in one column, the one right beside it happened 5 minutes later, or whatever your time interval is. We can also add more structure, though, by rearranging the events. So if we put events that are related to each other through correlation closer to each other, now we end up with an image in which every single cell has some type of structure in both dimensions. It's related to everything nearby, just like in an image of the real world is, right? If you have a color in one pixel, it's probably going to be similar to the pixels right around it. So with our feature sets that have so much structure in both dimensions, we want to take advantage of that with a modeling methodology, a modeling algorithm that can actually look at that structure as well. So image classification is a really, algorithm is an obvious thing to apply to this. So now that I've gone over what the solution is, how you can do this yourself, some of the methodology behind it, I'm going to talk about some results that we had from our own experiments. I can't divulge exact accuracy numbers for our games, but I can give you some overall trends and interesting things that we saw. So what we did was we looked at users who install their games, and we looked at all their actions after their first 30 minutes. And the question is, from looking at just 30 minutes of data, can we predict what happens 7 days later? Did these users come back to our games or not? And I'll start off by showing you a really cool graphic. So this graphic represents the difference between two populations. It's the people who did end up staying minus the people who left. And you can see a couple of interesting things here. The first is that you can see some differences. If this were just a flat graph, there wouldn't really be many events that you could use to predict the difference between new installers and not. So this is a really good sign. If we can visually see a difference between these populations, then hopefully the machine learning algorithms can pick up something, and there is some predictive value here. You can see that there's only a handful, or maybe 10% of the events that have a significant difference, though. And then you can see this huge flat area in which there's not much difference between the people who retained and the people who churned. So that tells you that if you chose the wrong events by hand, you might not really have much of a prediction there. But I think the most interesting thing is in the bottom right corner, you can actually see some negative events. So these are actions that people who quit the game did, a lot more than the people who stayed in the game. So what could these actions be that led to people quitting? What they did was they experienced errors very early in the game, and then they didn't come back. So you can see in the bottom right some of the error events that we captured in our clickstream. They're very negative, and that indicates people who didn't come back experienced them early. But then after the first 5-minute mark, you can see they actually increased. So these were people who retained in the game and actually experienced a few errors. They played a lot more, so it's more likely they'll experience an error. But they still came back 7 days later. So it tells you that experiencing errors very early after installing is a bad experience for users, which is somewhat obvious, but still interesting to pick out here. So we applied this to our models. We applied a few different models to this type of data, and we had some mixed results. The first thing we tried was simple linear logistic regression. And this had very poor results for accuracy, which is to be expected. Logistic regression treats all of the input variables as independent. It didn't pick up any of the structure that we worked so hard to embed into this data set. The next thing we did was random forest, which is very easy to apply using Spark MLlib. And that actually did really well. So random forest is a tree ensemble method, or uses a tree ensemble, and that's able to pick up more of these relationships. So we had some very good success with that, and it performed nearly as well as some of our models that looked at days of data. So it's very encouraging. Now, a deep neural network with image classification type techniques, you'd expect that to do the very best. So that's kind of a work in progress for us. We haven't had time to dig too deeply into there. It's something where I think you need a custom network, though. Some of the some of the networks and some of the structures that have been set up for real-world images might not work so well for this, because these aren't real-world images. But the ideas are going to transfer through. So that's something that's kind of our next step to look at internally. And I've given you one example of how to apply this technique, which is to apply this to your new installers and make predictions on whether they're going to come back or not. But there's a few other things you can do with it. For example, you can look at much longer time frames. There's no need to limit this to looking at minutes of clickstream data. You can look at your longer-term users and try to dig out some really interesting facts about how their actions are relating to their outcomes. You can also dig into these events a bit more. So we looked at one thing where experiencing an error led to poor retention, but you can use this to dig into even more and dig deeper into that funnel to see what's leading to poor outcomes or good outcomes for users. And finally, I think this can be used as a very powerful data set for user clustering. So you can use this to look at how your users are behaving and try to segment them that way. So you can look at this as time. For example, someone installed their game and they started playing single-player battles, and now they've transitioned over the weeks to multiplayer or something like that. With this type of data, you're able to pick up those types of clusterings and further segment your users. So at the start of this talk, I said how this is inspired by DNA microarray analysis. And this heat map right here is not from a video game. This is from a DNA microarray. So one of these dimensions is different genes, and the other dimension is different chemicals that are added to the microarray. And then it's lit up based on whether the gene interacts with that chemical or not. And they use clustering to figure out kind of clusters of genes that are related to each other. So it just kind of goes to show, like, you never know where your inspiration is going to come from for coming up with new techniques. And that's it for this talk. I hope you're now not afraid to work with the Clickstream data, and you can dig into your own user actions and make your users' lives better. I'd like to give a special thanks to my teammates, Mehdi Ben Ayed and Jijun Chao. I couldn't have done this without them. And now I'm going to open the floor to any questions.
Wonderful. Thank you so much, Patrick. All right, let's have some questions.
It's a great talk, by the way.
Thanks.
You mentioned using hierarchical clustering to rearrange things so that the features that are correlated are adjacent. But presumably that doesn't make a difference with random forests because you're going to unroll everything into a single vector.
Yeah.
That's something that might help with CNNs and so on later, right?
Yeah, and possibly some of the segmenting as well if you were to apply more clustering on it. So it's true for that, yes. The random forest would be able to pick that up regardless of how the different events are arranged.
Cool. I just wanted to check I hadn't missed something there. Thank you.
No problem.
How do you deal with when the app is constantly changing and new events are being added?
Yeah, so the nice thing about this framework is that it's just generating the heat maps based on what it reads from the actual Clickstream data itself. So it's kind of a two-step process. The first is looking at what events are present in the Clickstream and determining what are the top events to output. And then after that, it will go and generate these heat maps once it gets some of that metadata. So that first step kind of picks up any new events that happen.
When you train your heat map, how you come up with the labels? Because each event is different between the games. Do you have normalized labels somehow?
So we would generate kind of a heat map on a per game basis. You wouldn't have a heat map that mixes events across games, or that's not something we've tried. But is that what you meant by your question?
So you don't have like trained models that can work against all of your heat maps. So you have to do it trained per game.
Like, you're saying like if a user installs more than one of our games.
Yeah, or different games. So come up with your prediction base if they play game A, but you can come up with prediction for game B.
Yeah, we didn't extend it to examining multiple games at once. So we were just looking at actions within one game at a time. Yeah.
All right, one in the back.
Hi. Did you consider different, how did you pick your time windows, like the sizes of each bucket? And did you consider uneven distributions, like, 5 minutes, 10 minutes, 20 minutes, exponential, something else? How did you think about this? And did you experiment with other types?
We experimented with a few different ones, like looking at 60 minutes, looking at 10 minutes, but it was very coarse-grained. And like I mentioned in the talk, I think it would be more fruitful to maybe look at finer-grained at the start. So that's kind of a big space to explore, though. So we didn't have time to kind of find the optimal solution for that. But I would suspect that it would be better to look at 1 minute intervals at the start, for example, and then expand it. It'd be able to cut down your data a lot, too.
Thank you.
Sure. Anything else?
Any more questions?
No?
If not, let's give Patrick one more round of applause. Thank you.
Thanks, everyone.